Now, my pleasure to introduce Ed Lewis, talking about security, and good morning to everyone, too.
Okay. I'm going to talk about DNS security, or DNS Security Extensions, which is something that's been going on for about 4 or 5 years worth of engineering right now. And first thing I'll start out with is, in DNS in general, there are a lot of changes coming to DNS right now. DNSSEC is one major change to it. Dynamic update, being able to change zones on the fly, is coming along with securing that, and I'll talk about that part. Also, IPv6 is causing some changes to the name servers with the A6 record and the binary labels for reverse mapping. And also some other improvements, such as EDNS 0, which will help DNS work better, and other software improvements that are going into the next round of releases. DNSSEC is comprised of 4 ingredients. First one is the DNS Security Extensions, which are the key and SIG records, the NXT records, and they're generally involved with securing name servers to name server communication. The next part of the DNS security suite is what I call query response security, and that involves securing queries from resolvers to name servers, zone transfers, and also dynamic update would fall into that area. And that uses 3 different resource records. They're all meta records. And finally, or thirdly, serving security data. DNS will be able to publish security certificates and also public keys for your use. It's not exactly, I wouldn't call it a security server. It's just putting data out there for people to retrieve. And finally, dynamic update security is being added now to allow dynamic updates to come in and be trusted, be authorized, and also have make sure the updates are correct. Features that these 4 ingredients are offering. One is a protection of the internet scale data transfers, and that means when you query a zone somewhere else on the internet, we have to use one type of security to be able to make sure that you're getting the right answer from the right server. The next part is protecting local DNS transfers, that, as I said before, zone transfer, for example, where you're not going very far. You're going probably from a server you control to another server you control. And in that case, we want to do something a little bit more efficient than what we do for local security. A public key infrastructure is a feature where we're giving out keys, for example, and certificates. And also, we are now going to add security to dynamic updates. Right now, the DNSSEC is defined in a few RFCs. 2535 in the Internet RFC series is the primary definition of DNSSEC. There are a couple other RFCs that are associated with that. At the end of this presentation, there's a 2-page bibliography which lists other RFCs to see. I think I actually didn't list every one of them, but just put the range down. And the primary implementation of DNSSEC is, of course, or DNS is bind, ISU's bind. Right now, we're working on version 9. DNSSEC first appeared in bind in version 8.2 last March. And right now we're up to 822P5. I think 823 is due sometime in, I don't know when. What's in there is the ability to at least play with DNSSEC. It's a good place to learn DNSSEC. I don't know if we'd recommend anyone operationally using DNSSEC in those servers yet because we really weren't ready in the 8.2 to add DNSSEC. Beta 9, or version 9, is a brand new build from scratch in which DNSSEC will be fully implemented. Right now, Beta 3 has been out there, and of course being a beta, they're not fully functional yet. You can get an idea of what the real beta is, the real bind 9 is going to look like. And Beta 4 is due real soon now. I saw that there was a code freeze on now, so probably by the end of this week, if not today. The protocol right now is being worked on in two IETF working groups. DNSEXT is looking at some of the refinements of the protocol as part of its charter. Right now it's a proposed standard, which is the first of the level of standards for the IETF. It still needs some work to get to full standard, especially what's missing is operational experience. And that's what I've been trying to promote the last year or so. DNSOP is another working group which is looking at operational issues with DNS now. Both of these groups are fairly new. They're about maybe a year old each. And under DNSOP, I've done a couple of workshops to try to look at the protocol. And the workshops are mostly for my benefit and the protocol's benefit, because we have to iron out some of the difficulties, some of the things that we're not sure of right now in the protocol. In terms of just training people and using DNSSEC, we're not there yet because the tools aren't completely finished. And the questions we have now are how to operate this stuff, and also what policies are going to be used, how are you going to trust the data out of DNSSEC. Those things really haven't settled out. There are a lot of ideas on how to do that, but no consensus has been built. Now, in terms of deployment of DNSSEC, again, so kind of like IPv6, Europe is very much interested in this. I've done workshops over there. One of the there's a joke in here somewhere. Hello? Okay. One country is planning on having DNSSEC up and running by January 1st, 2001, and two others will be following within a few months of that. In CENTR, which is CENTR, which is a European, I don't exactly know how to describe it, cooperative group of all the operators there, have a DNSSEC working group to actually go in and do this. So they've actually been doing some testing with Bind 8.2 to see some of the performance plans we're going to talk about later, if they're true or if the fears are true or not. And they're taking a lot of action towards that. Also, there will be a working group or a workshop held in Japan under ICANN in next month. So again, Japan and Europe are looking at this more. In the U.S., I haven't been getting much in the way of interest in doing workshops. Root servers have looked at this. They're keeping an eye on this. It'll probably take some time after Bind 9 comes out before we actually trust this in the root servers. And the big thing here, deployment experience, is what we really are after now. I have a couple of slides here to talk about some of the DNS terminology to make sure we know what we're talking about when I describe some of the details of the protocol. In this slide here, I've got, let's see, there, sort of a diagram of how we set up some of the software involved in DNS. On one side here, we have the resolver. That's the client to DNS. It's what does all the lookups, and that could be either in an operating system, get host by name, or it could be part of another name server. Recursive servers are DNS servers which will take queries from resolvers and then do the lookup for that resolver. The recursive server usually does not know the answer initially, and will go off and do work to get that. Now, the idea here is that if a lot of resolvers sitting on one side here all want the same information, the recursive server will grab it for the first one, remember it, and hand it out to all the rest. We also talk about root servers, which are a set of servers that handle .dot and top-level domains in some of them. We talk about authoritative servers, which are servers which have information out of from each of the zones in DNS. We'll talk about that a little bit. Primary and secondary terms to refer to authoritative servers. And then I have other servers here because in the process of doing some of the lookup, you may go to lots of other servers. A resolver usually goes to a recursive server by default. It can actually go to any server it wants to if it just knows what the server is. DNS resource records are the fundamental unit of information. Up until DNSSEC, they could each exist individually. DNSSEC is formalizing the idea that they all travel together. For example, in this I have a name, myname.xy. All of its A records together are considered to be now a unit, it's a set of data. Zones versus servers is an important concept with DNSSEC. Zones are administrative cuts of the namespace. The domain namespace is built up in a tree. Zones are what part of that I administer. It could be a couple of domains, it could be a subset of a domain. It doesn't map one-to-one to domains. A name server is another thing which is serving information. So the zone is the administrative cut of data that you build up a database. The name server is separate, it sends the data out. A zone is served by more than one name server. A name server can serve 0 or more zones. It can have a server which just does recursive queries and caches information. So when I go on to the rest of DNSSEC, I'll talk about the DNSSEC part will talk about zone security. I'm going to talk about the zone data, signing zone data, passing zone data around. When it comes to queries and responses, I'm talking about the securing of communication from a resolver to a name server. The cryptography I'll keep to one slide. What's important here is there's a difference between symmetric keys and asymmetric keys. Symmetric keys are a situation in which you and I have a secret, and we do some processing on the same secret. We have to have the same secret, we have to communicate that to each other, and it turns out that is a pretty efficient way to do encryption and hashing of information. Public keys are another form of cryptography in which I keep a private key and I give you the other half of the key. And what I assign with one key, you can verify with the other key, and so on. In this case, distributing the public key is easy. I can put that out anywhere, and anyone can use that to decrypt what I say. The problem with asymmetric security, or asymmetric cryptography, is that it's slow. It takes a lot more arithmetic to process. One of the optimizations that we try to do is use asymmetric keys, public key cryptography, to launch into symmetric cryptography. And the other issues that will come into play with cryptography are patent controls and patents and export controls. And now I'm going to go into the specifics of the protocol. DNS Security Extensions is designed to protect data in which scalability is a big concern. Inter-server or resolver to server queries, mostly zone data being retrieved. There are three resource records that are defined to do this. One is a signature record, which will hold a digital signature over a set of data. The key record is going to hold the public key, which can be retrieved so that you can verify a signature, and also an NXT record, which is going to be used to indicate that data is not present. That would replace returning the SOA record in NX domain in a negative answer. This is a basic view of the syntax of the key record. Over here, OTC is the owner, type, and class. That's the envelope of the data. And this is what we call the R data portion of it, just showing that. Actually, I have key as the type. The first element there are the flags, and the flags basically will tell me what kind of a key this is. Their keys are used for a couple of things in DNSSEC. One is to actually verify the data in DNS. Another one we'll see later is it's used to create the query response secrets. And also, keys can be in there for the purpose of just being in there. It's conceivable that you could have an email key in there, or a PGP key or X500 key, or whatever kind of key you want to have in there. The protocol here indicates what the intent of this key was for. And there are a few values defined for that. I didn't write them down in the slides. I wanted to keep that detail out. 3, for example, is DNSSEC. A key with a 3 in there can be used to sign data, verify data, and so on. The algorithm indicates what kind of cryptography is used to do this. Right now, there is a mandatory to implement set of cryptography called DSA, Digital Signature Algorithm, or DSS, Digital Signature System. That's supposedly an unencumbered technology which everyone can implement in their name servers, and we can use that as one set of keys. Also, RSA, MD5, RSA, MD5, let's see. It's RSA, MD5 hash, I think. Say something wrong there. Anyway, that's another algorithm which is implemented, but that's encumbered. There's a patent over that. Fortunately, in DNSSEC, we have a license to use the RSA technology in name servers, so that's available. It's not mandatory to implement, so we don't know how to treat that exactly in the spec at times. It's also a bit more efficient than DSA when it comes to verifying data, which we think is probably very important in this in operation. And finally, the key bits are after that. The signature record is the most complicated of the records. It starts out with the owner, type, and class here, which I did omit this time. And then the next thing you see another type field, and that's the type that's covered. For example, this is showing a signature covering the SOA record. We have a few things here. We've got the algorithm again, which has to match the key that's used to generate this, so we know how to interpret the bits. We have the label count, which lets us know whether this was a wildcard or an exact match of the name. And then the original TTL. What's significant about this is that when data is put in DNS, it has a time to live put in by the authoritative servers when the zone starts. As the data is passed around, the TTL is decremented. Now, if you get data from another server that's not authoritative, it may have a decremented TTL. It's been ticking down a bit. I have to reset that TTL for the purposes of verifying the data to make sure the signature over here will work. That's at the end of this here. So I have to, when I do my verification, take the signature out, or take the TTL out, replace it, verify it, but then go back to the other TTL. One of the something that's going to be an operational consideration here is there is an expiration time for this signature. Up to now, DNS data has not expired. Zones can expire. Zones can't be, if they're missing, they can't be retrieved from a secondary from the primary. But now we have data which will actually go bad in the primary. So someone can't just set up a zone forever. They're going to have to go in there and change some of this off times if they're going to secure the data. So we have two periods of time, an expiration time and a start time. Having a start time allows me to put signatures into the future for purposes of rolling over keys. I may want to use one set of keys for today or this week, and another set of keys for next week, and I want to put the signatures out there when they're going to be used. The next two fields here, this one number here, and unfortunately I use a reverse map here as an example so you can't see separation so well, identify the signer of the key. This 39, 171, 99, etc. is the owner of the key record which will verify the data that's in the signature. This number in front of it is what we call a footprint, which lets me pick which key of those I want to use to try the verification. And finally, I have a signature at the end of this. Now, the third record in DNSSEC is the NXT RR. And this is used to link names in the zone so that I can show a ring of names and types. So that if I'm looking for a name and type that's not in the zone, I can look at this and say it obviously isn't there because I know what's in the zone. The owner of this, again, it's not shown. The first field here is the next name in the zone. And in this example, what I used was the root of the apex of the zone, which was 39, 171, 189, the delegation of the reverse map. And I know I did that because I have the SOA record present. The type bit map shows me what types are present at the name that owns this record. Probably a better way to view this is down in the corner here I have these loops. And at the apex I'll have a NXT record about the first name with what's present there and point down to the next name in the zone. And the next name in the zone I'll have what's there and then also point down to the following name in the zone. And when I get to the bottom of the zone, the last name in the zone, I point back to the top to make it a ring. Now, one thing that I don't think I have here, one of the implications of the NXT is that I've now created a ordering of names in the zone which we didn't have before. It's a bit of a change. Now, what I have here for the quirk of the NXT also has done the second thing in DNS. When I have a delegation point, I now will have two NXT records for that point. I'll have an NXT record as part of the parent zone, which says that, for example, if I'm in .com, if I'm A.com, I'm going to point to B.com. But I also have an NXT record belonging to A.com, which says I point to A.A.com in my zone. So what we've done now is now have two versions of data in different places that are authoritative in those zones. So the NXT has been a little bit of a hassle to implement. And there's some general dislike for the NXT. Some people like them, some people don't like them. One of the criticisms of the NXT is that it exposes too much information about your zone. Once I have the NXT records, I can go through your zone. Arguments like contrary to that is that your zone's public anyway, although you can't do an AXFR necessarily. And although we've recognized these deficiencies or these criticisms of the NXT, that does work. It's not really deficient. No one has been able to come up with a better solution to this problem right now. So it's out there, at least in the first release. Now this slide and the next are part of a zone, give you an idea of what the stuff looks like when I look at a master file. This first line here is the SOA record. That's the only record on this slide that would normally have been in your zone before DNS security. What I've highlighted here is a key record, to give you an idea what a key record looks like. the records get quite large. The cryptographical information is not short. The more secure your key is, the longer the key will be, or the stronger the key is, the longer it will be in data. On here, I've highlighted a SIG record. My mouse shows up. Which, the reason why I highlighted this one is that in this case here, I have 3 NS records for my zone. I have 3 name servers, a primary and 2 secondaries. I have 1 NS record to cover all 3 of them because those NS records are going to be held together as a set of data. So when they travel around, they'll travel together, and the signature will be sent with them to prove that these are the right name servers. And else, oh, okay. Let's see. Okay. So these 3 records here are being signed by this 1 record. Also, in here I have the signers, TSIG Karen Net. And if I go back a page, TSIG Karen Net is the origin, and it has this key. So this key here would be used to verify this signature over these 3 records. Also in here I have the NXT record, which I've highlighted down in here. This gray bar here, this is the first name in the zone, active. Above this is still part of the apex, the TSIG Karen Net name. Active is next, and then AMP is my next name in here. The NXT record here says after active, AMP comes following that, and present at this name is a C name, which says that this active in this zone is also known as active in another zone that I have. And I have SIG NXT in there also. Another example to change the DNSC names now can actually have certain other types in there, but just DNSSEC types. This is a schematic of how a query might happen. Queries can happen a number of different ways. This is just one possible way for it to happen. I have a client or resolver over here issues a request for an A record for host.example.xy. And my local name server here is just the name server the resolver knows. And I'm going to assume it's a recursive name server caching information for me. The first thing this name server will do, assuming it knows nothing about the answer, is it will go off to a root server and say, where do I get this information? And the root server, I'm going to assume here, which happens sometimes in operations, has the root zone plus also the CCTLDs or the top-level domains. And it'll send back here an answer saying that to get host.example.xy, you have to go to example.xy. And so my resolver, which is part of recursion, goes off to this other name server and gets the data I want, which is the way things used to work, and I'd be done with it. But I also get a signature of that record, of that set of data, signed by example.xy itself, and so I'll get any additional data, the key record, and the signature of that key by the next zone up. Because I probably won't be trusting example.xy's key without any pre-knowledge. I may know the root's key, but nothing else. So what happens now is I have to go off in this name server here, ask for the key for XY to be able to verify that signature. When I get that back, I get the key, and I also get the signature of that key by the root's key. At this point here, the name server will go off and go to the data saying this data is signed by, or it could go either way, top down or bottom up, depends on the implementation. When I have the data, I look at the signature of the key, say, okay, assuming that key is okay, the data is okay. I go up one level and say, well, is this key okay? I check it with the previous signature and key until I get back to the root key, which is what I've trusted because I've configured that. And finally, when this happens, the local name server will have verified the data and sends the data back to the resolver. This is what the DNS security, DNSSEC operations are that I've been describing. This is how they play out. What's happening over here is something I haven't talked about yet, the query response security, how we verify that part. Now, in order to go secure, what happens to an existing zone is that I start with the zone as unsigned. I first have to create a pair of keys, and if you pull down the bind releases 8.2 and on, there'll be a way of creating keys for a zone. What's important is that the zone keys that you generate, the public keys, have to be verified by somebody else, a third party, so that anyone else can trust them. Once that trust is set up, once that zone, the key is validated by the parent in our example, I can pass that around and people will start trusting it. After I have that set up, I can do the signing of the zone. I generate the signature records. And then finally, the NXT and SIG NXT are all also generated for the zone. Now, the last two steps in this process are done by what's called a zone signer. And there's a zone signer for bind 8 and there's a zone signer for bind 9. Now, once I have a signed zone, I can load it, and it looks like a regular zone in the name server. Now, when I'm running, I pretty much covered this already, that the query comes back with the desired sets plus the signature and any other data I need to verify that signature. So, query response security. This is another set of work in DNSSEC, what started as DNSSEC, where we're more concerned with the processing power than we are with scalability. For example, if you have a resolver going to a preferred server, I can set something up between that server and that resolver to trust each other more efficiently. Zone transfers are a big example of this. I don't want to have to use public key signing on a zone transfer all the time since I know all my secondaries. Something I'm not letting anybody just go get zone transfers. And also dynamic update. I'm going to need to know who's doing my dynamic updates, so I'm going to be able to set up a secret with them ahead of time. And what's introduced here are 3 meta records. These are records that are used in messages, but they don't end up in the DNS data space. A TSIG is a keyed hash covering an entire DNS message. A DNS message is traditionally the header, question, answer, authority, additional section. That's the original part of the format. TSIG doesn't change the format. It adds another record at the bottom. The meta record is at the end, and it's basically some information about the TSIG and a keyed hash in there. It's not a signature, it's a keyed hash. The effect pretty much though is the same between the two. One of the issues with TSIG, since it's a shared secret as opposed to public key, is that I've got to put the shared secret in 2 places, the name server and each resolver that's going to be involved with that one particular shared secret. In the name server, we've been able to solve that through the name, for example, in bind nameb.com. That file would now have to be unreadable by the general public if I have secrets in there. The problem we've had so far, though, is in the resolver. Where would we put something that's secret in the resolver? Because resolve.conf in the Unix world it's got to be publicly readable for any resolver to see where the name servers are. TKEY, I'll talk about in a little bit, is a proposed method, though, for coming up with TSIG on the fly, so we don't have to store that anywhere but in memory. We can work with that. As far as TSIG early on, we see that mostly in things like in zone transfers. That's the easiest place to use that. We've been using that already. And also special clients, DHCP updating is seen as an early place to put this. And we see that the growth in this will come later on. To give you an idea what TSIG looks like in a configuration file, I have a primary server and a secondary server, and I just put the secret in both places. And the secret I've used here is a valid secret. It's encoded in base64, which means that you can use capitalized, lowercase letters. You can't use any phrase. There's a restriction on what kind of phrases can be in there. This one works. It's the right number of letters. It has the right ending letters and so on. And the algorithm that's in there is the only one that's implemented at this time. And then we have to tell the servers, after we have the key up here defined, these servers are told, this server here, which presumably is .46, is told that when you talk to .35, use that key. And that's how a TSIG is configured. SIG 0 is something functionally equivalent to TSIG. It is actually the one it is the message authentication method defined before TSIG in time. It's defined originally in the RFC, which I'll get to in the next page, and it just works differently. It works on asymmetric keys as opposed to shared secret. That's the difference between the two approaches. Again, it looks the same. Syntactically, it looks the same in the message. SIG 0 is defined in RFC 2535, and we're updating that part of the RFC along with a few other parts of the RFC. SIG 0 requires that there be a public key in the zone for the resolver, and that the resolver has a secret there. There's a little bit less of a problem in using this because you don't have to have the shared secret sent back and forth between all of the pieces. Notice the name server doesn't have to remember the shared secret for all the resolvers. It has the public key. It's already in DNS. The problem, though, is that this doesn't have the performance of a TSIG has. The TKEY is the third meta record for query response security. Its purpose is to request a TSIG be set up. And what happens with a TKEY is that I'll send a message in as a resolver and ask the server to set up a TSIG, and some information has to go back and forth. Generally, this message should be signed by a SIG 0. For purpose, I'll get into the next slide. And what's happening in this case here is that if I rely on SIG 0 to start the TKEY process, I'm starting with the public key. The scalability problem is less of a problem, but I have the inefficiency of the processing. I use TKEY to generate a TSIG, which can last any amount of time on the resolver and the server. So it's a bootstrap into TSIG. A TKEY can happen one of four ways. I take that back. It's defined to be one of four ways. One is through a Diffie-Hellman exchange, which, if you're familiar with cryptography, is a method where you could take public keys and private keys at two ends and agree on a shared secret without exchanging any information about the secret itself. The next one is Microsoft has defined in Windows 2000 GSS API as a method for generating a shared secret. And then there are two other definitions of how this can happen, but there are no implementations. And that's where the client says to the server, I want to derive this secret and use it, or the client asks the server to say, give me a secret to use. Now, since in that case one side's deriving the secret by itself, the secret has to travel over the wire. In that case, it has to be encrypted. And when we get into encrypting information, we have all sorts of export controls, and so that stuff has never been implemented, just in the definition right now. So the TKEY, the result of this is to get TSIG set up, but there's one caution with a TKEY situation. Because the TKEY can request the server to go off and do lots of processing. When you're doing Diffie-Hellman exchanges, for example, the server has to go off and think, do some arithmetic. If the TKEY comes in when it's not signed, you could end up posing a denial of service threat to the server. So we want to make sure that you're signing the TKEY request before anything happens. Okay, this is the third part of DNSSEC, the securing security data server. DNS can provide a publicly scalable, redundant method for publishing security data, and certificates and public keys are the two pieces of data that would fit in there. Over time, I think certificates have become a lot more important to this than the public key in the DNS because of the limits of what DNSSEC does in the way of validation. DNS can say, here is what was given to me to give to you. It's kind of just saying this is what was mailed to you. DNS security doesn't necessarily go in and do any kind of verification that this really was the right key from the right person and so on and so forth. It's just that this is what this person told me to give you as his public key. And so what I talk about more here is the certificate part than the key part. The CERT records are a means to bind a public key to an identity with certain conditions, and certificates can be defined under things like X509 or SPKI or PGP are the three formats recognized in DNS. Actually, what's happening is the certificate itself, the format certificate encoded here, the way that's encoded is defined by the certificate itself. Whatever the other certificate system wants to put out in binary, DNS will hold. DNS only knows that in this CERT type field, what kind of certificate is supposedly encoded in there, so that if you were to grab certificates for some name that I have in DNS, I may have PGP certificates, I may have X509, and you only want to know to read the ones that you need for the purposes that we're talking about right now. Two other fields in here are the key footprint and the key algorithm, and this is used to link the certificate to a public key. In some certificates, you have to have the public key separate from the certificate. And so presumably I'll have it at the name I have here, a certificate identifying a public key and some information about my use of the key, and then we'll talk about a particular key that I also have at the same name. Now the fourth part of DNSSEC is the securing of dynamic update. This is still in definition. The implementation of this is one of the later parts of coming out with Bind version 9. There is a proposal or an idea out there called Simple Secure Update, which is a replacement of an earlier proposal for securing dynamic update that hasn't progressed to RFC, but it's still being implemented into the name server. The approach here would be to use TSIG or SIG 0 messages to cover the updates. And the theory here is that the resolver is talking to the name server as opposed to the zone. It tells the name server, here's what I want to do to the zone that you're holding. So the name server will talk to a resolver back and forth to make sure that the request is correct and from an authorized updater. Once that data gets into the name server will then hand it to the zone. The zone will then have to sign the data again with the zone key and put that online. Something I should mention here is that one of the big issues here is the great granularity of this policy, because not everybody's going to be allowed to update everything in the zone. I don't want to let a general user throw an NS record under their name. I don't want to have them delegate a new zone to themselves. So we're looking at what we allow general users to do and what we allow other special entities to do. An administrator might be able to add an NS record on the fly. Okay, I have a few slides here to talk about the impact of DNS security on name servers. DNSSEC will increase the attention that's being paid to DNS for 4 reasons that I have here. One is that data is actually going to expire from the name server. The signatures will go away. When signatures go away, the data will no longer be handed out as being secure, and so it won't be trusted. So it'll look like your zone may disappear if you don't keep the data up to date. So you have to make sure that you know when it is you signed your data last, how long you signed it until the next time you have to go through it. And in particular, if you sign parts of the data at certain times, some of the zone might go bad if you don't keep up with that. Delegations are going to have a recurring relationship, and this is the highest issue right now in terms of operations, is what that relationship is going to be. Administrators are going to have to manage keys. Now we have new cryptographic information that the administrator has to hold, and there are new issues that will come in on this. For example, where do you put the private keys? Who has the private keys? It's like the root passwords, but a little bit more in volume, I guess. And finally, there's a need for more resources to run DNS security. As far as delegations, the important part of delegations for DNSSEC is that when I delegate a zone to somebody else and let them run it, and they're going to sign the data, they're going to generate their own public keys. I have to figure out how I'm going to have the child zone's public keys continually be signed by the parent, because the parent's not going to sign the key forever. I'm going to sign the key for maybe a year, a month, a week, or so on. When the parent's signature goes bad, the child has to get a new signature. And how is that going to happen? Right now we're envisioning that the child will request a signature from the parent, put the onus on the child to remain secure. Also, the parent has to be able to say something to resolvers about the child's security status. And that's the most sticky issue right now, is how do we have a parent say, this child is secure, this child is not secure, and so on down the line, so that we can do the resolver queries correctly. We're working on trying to automate some of this. And some of this work we've been doing, as pointed out to me in discussion yesterday, was that we've been looking at this from the top-level domains as opposed to the mid-range or bottom parts of the tree, where there's more delegations than there is data, as opposed to places where the delegations are more informal. So we spent a lot of time trying to automate this for a very widely delegated zone. We need to look at some other issues of this. And this is something where workshops would help us identify what are the other requirements. And I have kind of a naive question here. Will this need to have a recurring relationship between the delegations to keep the registry info current? And what I mean by registry here is I think of DNS, not the who is database. And I'm not so sure that this is actually going to solve the problem. I'm basically just raising the question anyway. But we've had a lot of situations nowadays where domain names are getting hijacked through other methods, where the inter-registry protocol is been causing problems, not the DNS security. So one of the things referred to in DNS security is something called offline signing. And this is a situation now where I don't just process my zone on the servers. Right now, your zone data could be on a database that's publicly accessible. You just send that data, or accessible, but it's on the network, but and you have restricted use of that database. But you can generate master files from that and just load them up right away. When you have keys, you want to keep the keys as far from the network as possible. So you may have to have, it's desirable to have an air gap or something, or a firewall between where you do signing and where you publish the data, so that if someone does go in and hack your name server and breaks into the name server, they can't get the key information so that they can sign your zone with some other data. And one thing that's probably not been pointed out too well here is that if someone breaks your zone they break into all zones below you. So if someone steals com's key, they've got all this data throughout the DNS, or throughout the com world of DNS. Now, some of the concerns we have with performance is that we're going to use a lot more resources to do this because we're doing more work. One is the increase in the amount of data held. When I have an A record, I have a few bytes of data. If I sign that, I'm going to sign it with I'm going to leave a signature which is much bigger than the A record. So if you have one A record per set, you're going to have a SIG record which is much bigger than that A record, and so on through the zone. TCP right now may be used more if eDNS 0 isn't in place and working, which it will be there, because I'm going to need I'm going to have bigger responses coming back. And right now, if I get truncated responses in UDP, I go to TCP, and that causes a big overhead on the server. And CPU cycles are going to be used in doing the cryptography, the cryptographic operations. Now, in terms of verifying keys, going up to the root, I'll need more queries because now I can't just get the data I want. I need all the keys that I will need to verify that data going all the way up there. So, what I have here in 2 slides here, I'm about the end of this already. These 2 slides are a bibliography, and all of the URLs here I've checked as recently as the end of May. First one are the RFCs that are used to define DNSSEC, and then there are 2 up in here. TSIG just went to RFC in the last couple of weeks, and here are the 2 working group pages which describe the work that's going on currently in the IETF. And these are current drafts right now, give or take a 0001 at the end of these. They're up to date today, which describe some of the more recent enhancements. I think a couple of these are actually in working group last call in the IETF. These are other documents which are not necessarily IETF related that talk about DNS security. There's a paper from NAI which describes this in English as opposed to drafts and RFCs. It's still current in description, but some of the links some of the references it has are out of date. And then here are some pages. These 2 were workshops that were done last year, which have early versions of this presentation and others I've given. And NLNet Labs, which has been doing a lot of work recently in working with DNS security, has a page dedicated to DNS security of other resources they found too. And Cricket Lou has been working on some of the DNSSEC. There were some pages we found in Danish. The first page is in Danish. The links off of that are in English, talking about DNS security, and that was, I think, about 1998. And down here I have URLs for bind. That's bind version 8, the first URL, and bind 9 is the second URL, and that's where the betas appear when they come out. So I think that's it for me. Guess we can open up for questions. No questions. We're done with DNSSEC then.
I didn't have a question, but I wanted to answer a question that came up in the presentation. 823 is late. The reason it's late is not just that I am a slacker, but rather that we wanted it to be the last version of bind 8. And so every time we think that there is some minor thing that needs to be checked into, we sort of delay another few weeks while we check into it. This turns out, I think, to have been the wrong strategy. So 823 beta 5 is in every way better than 822. So I think we're going to put a cap on it soon and announce that 823 will not be the last bind 8, so that we more or less have room to add more in the future without delaying the release that's in progress. And as for bind 9, there is another beta coming out, I think today, the beta 4, and we are running it in production on a number of internal systems at ISC. So one of the things we've noticed is that it takes a smaller memory footprint to represent huge zones. Another is that the multiprocessing actually works. So if you have a thread-safe machine and multiprocessing with good kernel-supported threads and whatnot, such as any of the mainstream Unixes like Solaris or Digital Unix or whatever. It will use all the CPUs, and it balances nicely, and it scales nicely. So I'm not saying run right out and move all your name servers to it, but I am saying it's time to grab the beta and get some experience with it, because it will be in full public release soon.